Hi, this is the next video on functions. So in the last video I sketched lots of graphs and talked about the domain and range of each graph. So I'd like you to first of all pause the video and try and sketch those three graphs. Okay, so this one you would complete the square, so -9 minus 2 is -11. The domain can be anything, so your turning point is at -3, -11 here. So it's going to look like that. So that's at -3, -11. Okay, no other restrictions, so the range has got to be greater than or equal to -11. This one here, reciprocal, x can be anything apart from 0, and that's because of that. So this has got an asymptote at -2 and at x equals 0, down there like that. So that graph is going to look like that, going down there and down there. So y can be anything except where it's -2. And then this one, well, this is an exponential, it's 3 to the x will be that way, 3 to the minus x is going to be that way, and then there's going to be an asymptote at 3. So that's y equals 3, and it's going to go like that through 4. So that's what the graph looks like, which means that the range can be anything as long as it is greater than where the asymptote is, which is 3. Okay, so you need to know, you need to have a really good understanding of how to sketch all these different graphs. So hopefully you've had enough practice. Okay, we're just going to carry on with sketching, but there's some different ones that we need to have a look at. Now this is called a piecewise defined function. So if it looks like this, with 2 separate bits or 3 separate bits, it's called a piecewise function. So if you look, for x is less than 1, we've got a line, and where x is greater than or equal to 1, we've got a quadratic. Okay, so there's going to be 2 separate little bits of graph that make up that one function. So we need to, first of all, we need to sketch it and state its range. So I'm going to start off with x equals 1, and I'm going to draw this bit first. And I know this is a line. I know that it goes through 5 and has got a negative gradient. Okay, so we know in my mind it looks like that. So when x equals 1, 5 minus 2 is going to be 3. So when x equals 1, y is going to be 3. And then it's going to go that way. Okay, so that's going to be the smallest value, and then it's just going to go up like that as a straight line. And that's going to be at 5. This one, I know in my mind, looks like that. Okay, but obviously some of that is not required. So I do know that it's going to turn where y equals 3. So that quadratic, in fact I'll just draw it in, dotted for now. That's going to look like that, roughly. That's at 3. But we only want where x is greater than or equal to 1. So all of this has to go really. So the smallest value on that quadratic is going to be where x equals 1. So where x equals 1, y equals 4. So that was the point 1, 3. The quadratic, its first point is 1, 4. So that's there. And then it's just going to get bigger, where x equals 2, that's going to be 7. When x equals 3, that'll be 12, and so on. So it's just actually going to just be that bit there that we're interested in. Okay, so you need to know the shape and consider particular points. Now, if you look, there's a less than and a greater than or equal to here. So this one is only valid where x is less than 1. So just to distinguish from an equal to, I'm going to put an open circle here, just like you do on a number line. And this one, well, y can be 4 because x is greater than or equal to 1. So this one is going to have a closed circle. Okay? The smallest value is this y value, is this one here. So this is where y was 3. So the range is going to be based on this, but y is not equal to 3 here, is it? Because x isn't equal to 1 here. So y has got to be greater than 3, but not equal to. Okay, so it's a bit more complicated. You've got to know what each shape is and consider particular points and the restrictions of the domain. Now, one thing to say, this is a valid function because there is one y value for each x value. If that was coloured in there, then that would no longer be a function due to the fact that there are two x values that give the same, it would no longer be valid due to the fact that there is an overlap. Okay. Equally, if there was a gap, so if that, for example, started here, so if that said 2 there, then there would be a gap in the x values, okay? And there's got to be a unique y value for all x values. So we can't have a gap. So just be aware of that. They might give you what looks like a piecewise function, and they might ask you to say what the problem is with it. So if there's an overlap or if there's a gap, then that cannot be considered to be a function. So just something for you to think about there. Okay, part B says solve f of x equals 19. So solve where that function equals 19. Well, if I draw on the line y equals 19, let's say it looks like that, then you can see there's going to be two solutions, one where the line equals 19 and one where the curve equals 19. So if I put the line equal to 19, let's move the 2x over, take the 19 and divide by the 2. So that is where x equals minus 7. Then I need to put the curve equal to 19. X squared equals 16. Now x technically can be plus or minus 4, but in this case it's not going to be minus 4 due to the fact that x is not negative for that particular function there. It's got to be greater than or equal to 1. Okay, So those are our two solutions. So it's good to have a sketch so you can see which solutions are valid. If the sketch wasn't there, you could see which one was valid by going back to this domain here. Okay, so that's a piecewise function, and they crop up every now and again. The other functions that we need to look at are more complicated looking reciprocal functions. These have been quite popular in the exams of late, so it's worth just having a little look at. So these are graphs of the form f of x equals ax plus b over x plus c. Okay, that's what you're going to get, so something of that variety. So this has got a 1x, there could be a number here. We'll look at that in a minute. Okay, so we're going to sketch that graph. All right, it says in blue, what would be the natural domain for this function? So if there was no particular restrictions, unnatural restrictions, what would the natural domain be? Well, the natural domain would be anything except, in this case, where x is 3. Because if x is 3, this is 0, and you can't have something divided by 0. So x can't be 3. Now that should immediately tell you that there is an asymptote at x equals 3. So you should know just from that you have got an asymptote at x equals 3. Okay. Now this is a reciprocal graph, but it's not obvious what it is. So you've got two options. You can either just substitute numbers in and plot it, or alternatively we could write it in a different form and apply graph transformations. So I'm just going to show you that version. We're going to write it in a different form by basically doing long division. So I'm going to do x plus 2 divided by x minus 3. X into x goes 1. So divide, multiply, and subtract. Take that is nothing. 2 take negative 3 is 5. So that actually can be written as 1 plus 5 over x minus 3. So we've written it in a different way. Now this is a multiple graph transformation of 1 over x. So if you think about what's happened, if this was our original function, well, you've got x minus 3 has gone into the function. It's been stretched 5 times, and then it's added 1 to it. Okay, so if you think about 1 over x looks like that, with asymptotes here and here. So this is going to move it right by 3. So that's why that there has moved 3 to the right. Then there's going to be a vertical stretch times by 5. Well, that's not going to affect that asymptote due to the fact that 5 times 0 is 0. And then that's going to move up by 1. So the horizontal asymptote is basically just going to move up by 1. So in terms of the sketch, this number is pretty much irrelevant. It's this that's going to tell us that horizontal asymptote. So this is the vertical asymptote, which we get from the domain. This is the horizontal asymptote, which is going to be our range ultimately. Now you notice this 1, that 1 there, comes from the quotient. So what would, if there was a 2 there, what number would go there? Well, it'd be a 2. Okay, so this number here, really, in terms of sketch, isn't particularly important. This one gives you your vertical asymptote. Whenever number's here is going to be your horizontal asymptote. So if that was a 2, you would have a horizontal asymptote at y equals 2. So if we sketch that in, so that's going to go like that, in that first top left, top right quadrant, and then bottom left quadrant, like that. Okay, so the range, the domain is dictated to by this. The range then, well, the range can be anything, in this case, except where y equals 1. And the 1 comes from the fact that when you divide that by that, you just get 1 as your quotient. Okay, so that's that. So this was a naturally occurring restriction due to the nature of that graph. But what happens if we consider the same again, but there is a different restriction, and we've seen this a lot recently, where there's been a restriction. Okay, well, you've got 2 options. You can either go through this whole process and then just consider where x is greater than or equal to 4. So here, where x is greater than or equal to 4, well, when x is 4, this is 6 over 1, so it's just where x is 4, y is 6. And then as x gets bigger, so that's the point 4, 6, as x gets bigger, then it's just going to be that bit of graph there. So actually, we only need a little tiny bit of graph like that. Okay. The alternative, if you have a funny restriction, is just to consider what happens when x is 4 and bigger. So when x is 4, like I just said, when x is 4, y is 6. That's there. When x is 5, y would be 7 over 2. When x is 6, y would be 8 over 3. Okay, let's go a bit bigger. What happens when x is 20? Well, when x is 20, y is 22 over 17. What happens when x is 100? Y is 102 over 97. Where is this starting to converge to? When x is 1000, y is 1002 over 997. And hopefully you can see that this is, as x is getting bigger and bigger and bigger, y is converging to 1, which it is. Okay, but without necessarily drawing that graph, you could see that it's converging to 1. Okay, so there's two options. Either you need to consider the full graph by doing this and then restricting, or do this and consider what's happening. But you must at least be aware that this thing here is a reciprocal and is therefore going to be of this form. Okay, if there's a minus here, if that was x minus 2, then it would be in the other two quadrants. It'd be a negative reciprocal. Okay, ultimately we need to know what the range is. So the range, well, y can't be 1 or less, so it's got to be bigger than 1, but then when x equals 4, y equals 6, so therefore it's got to be less than or equal to 6. So they're quite complicated, these questions, but like I say, they are quite popular at the moment in terms of testing. Okay, so have a go, pause it, have a go at these two. Okay, we'll discuss the answers in the tutorial. What I want to do now is have a look at E and natural log in a bit more detail. Okay, so you talked about these in the previous topic. E is special because its gradient function is also the same. But E, in terms of a sketch, looks like any other exponential. So the domain of E is anything. The range of E, well, the range is restricted because of this asymptote. So there's an asymptote here. So the range of E is going to be greater than 0. E is a function because it is a one-to-one mapping. Okay, it's one x value maps to one y value. So I would like you to pause the video and try and sketch those three graphs. Mark on where it crosses the axes if you can, and for given the domain, which is the set of reals, write down what the range is. Okay, and then the inverse of E, as we've already talked about, is natural log. Natural log, just to remind you, looks like that. So you've got to remember what this looks like. So it goes through 1 there, and there is an asymptote here. The domain then of y, well, the domain is its possible x values. X can't be 0 or less, so x has got to be greater than 0. The range, however, this can just keep going up and up and up, and down and down and down, so the range of this can be anything. So notice how the domain and the range of E and natural log are switched. So the domain of E was set of reals and the range was greater than 0. These have switched positions. Mapping, well, natural log is 1-to-1. One x value maps to one y value. So natural log is also a function. So again, like you did on the previous one, I would like to see if you can sketch those, mark on the asymptotes, state the domain and the range for each graph. Okay, so now from the last 3 videos, you should have enough information to complete the questions on exercise 2B. That's the end of this video.